Yeah, my name is Fermi, and this is a joint work with my fantastic co-authors, Alex Lombardi and Nick Spooner. All right, so the motivating question for this work is understanding when are classical crypto systems secure against quantum attacks, or post-quantum cryptography. So a bit of a shift from the last talk where we were looking at quantum protocols. Now we're back in the classical land where everyone's classical except for the adversary. Okay, and before I dive into things, I want to clear up a fairly common misconception I hear a lot when working in post-quantum cryptography, is isn't this just all about using LWE? Like, why aren't post-quantum assumptions enough? Right? And the misconception is that for post-quantum security, all you need to do is take quantumly broken assumptions like factoring and then just swap them out for post-quantum assumptions like learning with errors. And the reason that this is a misconception is that this ignores the other components of a cryptographic security proof. Because when you prove a crypto system is secure, you need three parts: a definition, a reduction, and an assumption. And to get post-quantum security, all three of these components have to be quantum compatible. So you need definitions and reductions that also capture post-quantum security. And this can be surprisingly difficult or even downright impossible in some settings. Right, so this work, we specifically focus on zero-knowledge protocols. So it's an interactive protocol between a prover and a verifier. The prover is trying to convince the verifier that some statement is true. We require our usual completeness and soundness properties. So if the statement is true and the prover follows the protocol honestly, then the verifier should accept. If the statement is false, then even if the prover is malicious, the verifier shouldn't be able to accept, or shouldn't be able to make the verifier accept. And the sort of defining property of zero knowledge is the verifier learns nothing from the interaction. And this is formalized by saying that the proof of a true statement can be efficiently simulated without the witness. So we have a very deep theory of zero knowledge in the classical setting. It's something that we've been studying for almost 40 years now. And the question we're asking is, how well does this theory hold up against quantum attacks? So we're certainly not the first to ever ask this question. In fact, there are a number of positive results in the literature. But a cohesive theory of this is still pretty elusive. So just to illustrate my point, like even many textbook zero-knowledge protocols, some of the first ZK protocols that we've had, things that we teach in Crypto 101, we don't understand their security against quantum attacks. So things like the GMW graph non-isomorphism protocol, the Feiges-Shamir trapdoor extraction paradigm, things like this. So in this work, we have our contributions are mainly in two parts. First, the contributions on the definition side, where we actually revisit the definition of post-quantum zero knowledge, and along the way, overcome a subtle definitional issue highlighted in a recent work of CCLY. And the second half is on the reduction side, showing how to achieve these definitions, showing that the protocols from the previous slide actually are zero knowledge under our definition of post-quantum ZK. And on this front, what we have to do is show how to extract a witness, a classical witness, from a quantum attacker in a way that's undetectable, in a way that doesn't disturb its state. And as consequences of this, we show that graph non-isomorphism and this Feiges-Shamir paradigm are actually post-quantum zero knowledge. And in the paper, using a slightly different set of techniques, we also get results for the Goldreich-Kahan protocol. All right, so here's the rough plan for today. I'm going to focus on the graph non-isomorphism protocol as my running example. And I'll talk about how that protocol works, as well as how we prove its zero knowledge in the classical setting, using a paradigm called extract and simulate. And then I'll talk about the challenges in transporting this framework to the post-quantum setting. And then I'll talk about what we do in this work, both on the definition side and the reduction side. All right, so in this protocol, the prover and the verifier have agreed on a pair of graphs, G0, G1. And the prover is trying to convince the verifier that these graphs are actually different. Okay. So first, let me show you a slightly simplified version of the actual protocol, just to give you a taste of the underlying idea. Okay. So what the verifier is going to do is it's just going to pick one of the two graphs, G0 or G1, at random with this bit B. It's going to randomly permute the vertices and then send over that permuted graph H to the prover. And the prover's task is just to tell the verifier which graph it's sent. And completeness and soundness in one bullet are that the prover can distinguish these two distributions that it gets if and only if the graphs are not isomorphic. Right? If the graphs are actually the same, then the prover's view is just independent of this bit B, so it can't guess it. And zero knowledge, well, this protocol isn't the full protocol, so it's not actually zero knowledge. However, it is zero knowledge against an honest verifier. Like if the verifier does not deviate from the protocol, then it indeed learns nothing from this protocol. And that's just because the honest verifier samples a bit B, and then all the prover does is tells the verifier B, but it already knew that bit. Okay, so to get full zero knowledge, you need to show that the view of any even malicious verifier can be simulated. And the thing that malicious verifiers might learn from this protocol that an honest verifier wouldn't is this bit B. That's the only thing the prover sends. Okay. So in the full protocol, before the prover sends this bit B, they actually engage, the prover and verifier engage in a sub-protocol where the verifier convinces the prover that it already knows B. And only once the prover is convinced that the verifier wouldn't learn anything from the prover sending B does it actually go ahead and send that bit. Okay. So there's a proof of knowledge sub-protocol, these extra messages that happen in the real protocol, and this is how you make this thing actually fully zero knowledge in the classical setting. So the way this works, it's the verifier is going to take the two graphs, G0, G1, randomly or switch their order, where G0 comes first, where G1 comes first. And then it'll randomly permute the vertices and send these graphs over. Next, the prover is going to send a random challenge bit. And the verifiers, if the challenge bit is 0, the verifier has to reveal how these two graphs are permutations of G0 and G1. And if the challenge bit is 1, the verifier has to reveal how one of these graphs is a permutation of H. So the reason this works is that if the verifier can answer both challenges, so succeed in this protocol with better than 1/2 probability, then it has to know the bit B, right? Because if you saw the answers that the verifier gave to two different challenges, you could piece together that bit B, right? You could figure out which one of these graphs is isomorphic to H, as well as how they relate to G0 and G1. And so finally, if this protocol is convincing, so actually we have a parallel repetition of this going on, if all of those repetitions are convincing, then only in that case does the prover send the bit B. Okay, so this is how the protocol works classically. How do they show its zero knowledge in the classical setting? It's with this simulation strategy called extract and simulate. Okay, so what we have to do to prove that this protocol is zero knowledge is show that the view of any malicious verifier can be simulated. And if you go back and look at the protocol, the only tricky part in simulating the verifier's view is figuring out what bit the verifier is expecting to see in that last message. Everything else is easy to generate. So what is that last bit? How does the simulator figure this out without actually being able to solve graph isomorphism? So how does this work? Well, the simulator is going to run the verifier first forward. So it runs it to the up until it needs to send the last message. Okay. And at this point, it just checks whether the verifier is convincing in the sub-protocol. And if it's not convincing, it can stop here. This is the easy case. Right? If the verifier is not convincing the sub-protocol, the real prover wouldn't even respond. So the simulator can stop here. But if the verifier is convincing, the prover has to output this bit, and that's when things get harder. And now at this point, what the simulator needs to do is run the verifier many, many times on various challenges until it finds a second accepting response. And once that happens, then it can extract the bit B, right? Because that's the one property of the sub-protocol that we know, that if you have two accepting responses, then you can extract the bit B. Okay? So you query the verifier many times until you get two accepting responses, determine the bit B, and then you send that to complete the simulation. So that's the extract part. You extract B from the verifier, and then by sending it, you complete the simulation. And this extract and simulate template is not unique to this one protocol. It's a very common design paradigm in zero knowledge. All right, so before I move on, I just want to make one important point. We typically want to think of the simulator in zero knowledge as an efficient machine. Right? We want to say that anything the verifier learns can be efficiently simulated. However, this simulator is not actually a polynomial time machine, but rather it's an expected polynomial time machine. And that comes from the fact that it needs to keep running the verifier over and over again until it gets that second accepting response. And we don't know a priori how long that's going to take. However, in expectation, you can argue that this takes a polynomial amount of time. Because assume the verifier has an epsilon chance of being convincing in the sub-protocol, then there's only an epsilon chance that you ever need to go in that loop in the first place, right? If the verifier fails in the first try, you don't even bother. But in that epsilon chance that you need to go and get that second accepting transcript, it takes an expected 1 over epsilon steps to see another accepting response. So the epsilons cancel out really nicely, and you get an expectation this runs in polynomial time. All right, so what goes wrong with this in the post-quantum setting? Well, basically everything. So for post-quantum zero knowledge, you need to extract the bit from the quantum verifier. It's really unclear how you do that, right? So classically, we're doing this by rewinding the verifier to an earlier state. The problem is that if the verifier is now a quantum verifier, it may have some internal quantum states, and then recording its response could irreversibly disturb it, and it's not clear how you query it for more for more answers. And to make things even harder, not only do we have to extract this bit from the verifier, but we also have to do it in a way that simulates its internal state. It needs to be consistent with what it would see in the actual execution, where in the actual execution it's only run once forward. And it turns out that we do have techniques from prior works of Unruh and a work of Keza, Spooner, Zandri, and myself, where we show actually that there is a way to handle the first problem, that there is a way to extract information from quantum adversaries, but the way that these works do it very much relies on disturbing the state of the adversary. And it's not going to be enough for extract and simulate. And finally, you need to do all of this in expected quantum polynomial time. And the difficulty here actually turns out to be definitional, in that actually nailing the right notion of variable time quantum simulation turns out to be quite subtle and is pretty closely related to a bunch of definitional issues that arose in the 90s when people were formalizing the basics of quantum Turing machines. So I'm actually going to address the last problem first. What do we have to do to define post-quantum zero knowledge? And then after we handle this, I'm going to go back and talk about how we achieve this definition and do extract and simulate. So the question is, how should post-quantum zero knowledge even be defined in this regime of expected polynomial time simulation? So remember that the original definition of zero knowledge, in the paper introducing ZK, says that the protocol is zero knowledge if the view of any classical polynomial time malicious verifier can be simulated in classical expected polynomial time. Right, this is the definition you need for the previous GNI protocol to even be ZK. And in some sense, this is the best definition you can hope for, because the result of Brock and Lindell from 2002 shows that if you were to ask for a better simulator, one that ran in strict polynomial time, well, none of these protocols would be zero knowledge, that actually classical strict polynomial time ZK is impossible. So you would expect that maybe a similar state of affairs holds quantumly, that to simulate or to define post-quantum ZK, you'd want to say that the view of any quantum polynomial time malicious verifier can be simulated in quantum expected polynomial time. But it's not so clear. And in fact, this recent paper of CCLY shows that for a certain notion of quantum expected polynomial time simulation, well, zero knowledge is impossible. So what do we do in this work? Well, we give a new zero knowledge definition that circumvents the CCLY barrier. And it comes down to understanding what does, or how we should define expected quantum polynomial time zero knowledge simulation. And we formalize two different notions, one that we call measured EQPT and one that we call coherent EQPT. So a measured EQPT simulator is one that works as follows. It's a fairly natural definition. You have one designated halt qubit initialized to 0, and then the state that you're trying to run your computation on. And at every step, you apply some fixed transition function, transition unitary m. And then after that, you measure this halt qubit. And you keep going up until the measurement of the halt qubit is 1, and you stop at this point. Right? And we require that the expected number of steps this takes as polynomial. What CCLY show is that any measured EQPT simulator will inherently fail to simulate the verifier state. That actually measuring the simulator's runtime is going to get in the way of the nice coherence that you'd want to produce a good simulation, and this makes negligible accuracy ZK simulation impossible. So what we do is define a notion of coherent EQPT that at a very, very high level allows you to run a variable time computation in a way that avoids measuring the runtime. So there are several ways to make this notion formal, so let's try this one. One way you can think about it is imagining that you have oracle access to a unitary U that essentially runs the purification of a measured EQPT process for, let's say, some exponential number of steps. Okay, so if you take this very literally, U is just an exponential size unitary. But what you're doing is you're leaving the time register in superposition, but outside of the view of the person querying this unitary. And so at this point, nothing has changed. All I've done is purify the top of the slide. All right, so at this point, I have a superposition over different runtimes. If I were to measure t, I would get an expected polynomial. And it certainly looks like this is an inefficient computation, but it's exactly the same as the top of the slide. Even though U is an exponential size circuit, the amount of work it's doing is really expected polynomial. Okay? But so far, nothing has changed. So what is this coherent notion? Well, we let you do an arbitrary computation on the input wires. And then crucially later, you can query the oracle again to erase the runtime. So you leave the runtime in superposition, maybe extract the output that you want from the computation, and then later run the inverse of U and erase the runtime and set it back to 0. And what we observe is that CCLY's impossibility does not rule out the possibility of coherent EQPT simulation. All right, so maybe the immediate question then is, why is it at all reasonable to define post-quantum zero knowledge with coherent EQPT simulation? And to answer this, let me raise a very related question of why was it reasonable in the first place to define classical zero knowledge with expected polynomial time simulation? Well, there's sort of two reasons for this. One is that when it comes to breaking cryptography, expected polynomial time simulators are no stronger than polynomial time machines. In particular, if you have a crypto assumption that is broken by an expected polynomial time machine, it's also broken by a polynomial time machine. Basically, you can truncate the algorithm at an appropriate cutoff. Okay, so in terms of breaking crypto, EBT is no stronger. And it also is the weakest model that seems to make zero knowledge possible. Because if you ask for strict simulation, that's not gonna work. And we show that analogous state of affairs holds for coherent EQPT. In particular, that it's no stronger than quantum polynomial time, that if you have an assumption that's broken by a coherent EQPT machine, there is an analogous truncation argument that shows that there is a quantum polynomial time machine that breaks it. And moreover, coherent EQPT appears to be the weakest model that makes post-quantum zero-knowledge simulation possible, given the CCLY impossibility that measured EQPT simulation is impossible. All right, so that's on the definition side, but writing down a definition is not the end of the story. You actually have to show that these protocols achieve this definition. And this is actually where the bulk of the technical work in this paper is. So our goal now, back to this graph non-isomorphism example, is to build a coherent EQPT simulator that extracts this bit B from the malicious verifier without disturbing its internal state. And as a starting point, we're going to use this work of CMSE, which shows how to extract this bit from a quantum malicious verifier, but in a way that will highly disturb the internal state. So just to quickly recap what's going on in CMSE, there's a lot of technical moving parts in that paper, but the important points for this slide are that the way that this approach works is by considering a subspace of so-called good verifiers. And every time you query the verifier, you're going to kind of repair a state by amplifying back onto the subspace. So it allows you to sort of run a classical rewinding procedure where you query the verifier in random challenges, measure the response, and potentially disturb the state, getting this psi prime state. And then by amplifying the state back onto this subspace of good verifier states, basically verifiers that would have a good chance of answering you correctly in the next challenge, then you can keep running this procedure. So the way this works is that you just basically augment the classical rewinding procedure with just random queries and measurements with this additional repair step between every trial. And so with this in mind, the kind of natural thing to try for extract and simulate is the following. You consider a variable time procedure, which is basically run the CMSE rewinding algorithm until you get 2 accepting transcripts. And what we'll do is try to run this forward, produce the extracted bit B, measure that, and then uncompute everything. And when will this work? Well, the simulator won't disturb the state so long as this measurement that happens in the middle basically has a predetermined outcome. Right? We're doing a unitary measuring something and then doing the inverse of that unitary. So this does nothing to the verifier state so long as you can argue that that measurement you do is basically fixed. And for that, you need that the extractor succeeds at probability close to 1, and that the extracted bit is in some sense unique. And moreover, on top of these 2 bullets, you also need to guarantee that the simulator is efficient. You need that this extraction procedure is measured EQPT. So plugging in CMSE directly doesn't give you any of these guarantees. If you work for a little bit, it's not too hard to show that you can modify it to get the first 2 bullets to go through. But it turns out the really hard part is actually getting the last bullet, the measured EQPT guarantee to work. So let me say a little bit more about this. If you use the CMSE approach, you're going to get something that's very, very far from expected polynomial time. And the reason for this is basically inherent in the template of measuring and then repairing the state. So let's think back to the argument we gave in the classical case for why the simulator was expected polynomial time, which is that with probability epsilon, you run for an expected 1 over epsilon times to see that second accepting transcript. Now here, how long is that going to take? Well, with probability epsilon, you run 1 over epsilon trials. But for every single trial, you need to repair the verifier state. And that turns out to incur this extra 1 over epsilon to the 4th overhead. And now you've ruined that nice epsilon cancellation that happened classically. Like when epsilon is small, this can be unbounded. And well, this is really unfortunate because if you look at what this repair procedure is doing, there's basically like no chance that you would ever get a constant time version of it, which is what appears to be necessary for this to be expected polynomial time. So what we end up having to do is design a whole new rewinding template from scratch, where we abandon the usual approach of just querying the adversary on random questions and doing that until it gives us accepting responses. Instead, we're going to generate the accepting transcripts in a more quantum fashion. We're basically going to prepare a superposition of all possible challenges, and then take that state together with the adversary's states, and kind of amplify this onto guaranteed accepting executions of the adversary. So it's far from obvious like why you can still repair adversaries when you do this. It's far from obvious like how long this actually takes, but it does buy you a significant speed up. And then to put it all together, you need to combine this with a bunch of algorithmic optimizations that we borrow from prior work on the quantum singular value transform. Okay? So this one box is basically like 50 pages of the paper. There you go. All right, so conclusions. Definitions and reductions for post-quantum zero knowledge can be extremely subtle. In this work, we define post-quantum ZK with this notion of coherent EQPT simulation. And then we went ahead and built these simulators for various textbook ZK protocols by combining a bunch of existing techniques with new ideas for doing rewinding. So for future directions, I still think it's open to really develop a general theory of post-quantum zero knowledge. We have lots of protocols where they certainly look secure, but we can't prove security. And it would be really great to just get a better understanding of that that's like closer to our classical intuition. I think it's also really interesting to look at quantum communication zero knowledge. We don't know really what the possibilities and impossibilities are there. Maybe you can use weaker assumptions, fewer rounds, strict polynomial time simulators, who knows. A natural starting point for this are the works of Broadbent and Grillo, as well as the talk that you saw before this one. All right, thanks.
Okay, thank you. Do we have questions?
Thanks for the nice talk. I was curious, so it seems that at some point you said that you want to extract B, so the witness, and to be able to use this gentle measurement lemma, somehow you want to have a single witness. So how does it go for, like, I guess if you want to get zero knowledge on NP problems, usually you don't have a single witness. So can you prove zero knowledge proof on arbitrary NP statements, or you restrict?
Good. That's a great question. It turns out that actually in like a lot of these protocols, the witness is implicitly committed to already in the protocol. You can imagine that there's many witnesses, but if the prover has committed to the witness earlier in the protocol, then there might only be like one unique witness that you could extract. So many witnesses could exist, but as long as like the simulator would only ever extract one witness, essentially because it's fixed by the protocol, then you can show that these techniques work. And this sort of committing to the witness is actually like already present in a lot of protocols.
Okay, thanks a lot.
Do you expect this technique or a close variation of this technique to be applicable to non-interactive ZK protocols?
Probably not. Yeah, a lot of this is really tailored to the setting of interactive protocols, right? We're running an interaction backwards and trying again. But I've also been surprised many times before, so who knows?
Any more questions? No.
So in this work and your previous one on succinct arguments, it seems like dealing with the rewinding issue using quantum algorithms is sort of substantively very different. And I'm wondering if there are guiding techniques or unifying principles in what we even mean by these rewinding templates, and if it gets sort of significantly more complicated than the extract and simulate thing that was given here. Are there unifying principles? What do people mean when they talk about rewinding in terms of diversity of problems one might have to face with proving security?
Wait, just to be
Yeah,
clear, the
sorry.
question was that what do we mean by rewinding? Or?
It seems like the rewinding here and the one in your succinct argument paper are substantively different, and this required a lot more mechanics to solve. And I'm wondering how.
Yeah. No, that's a really good question, and I think that like the terminology is confusing. I have found this confusing many times. It seems like so rewinding is just like a general like umbrella term for sort of whenever you need to reason about like the security of an interactive protocol. But most of the like specific examples of it fall into like one of two categories. One, when you're trying to rewind a prover in an interactive protocol, and you're using this to argue soundness. And usually what you do in these kind of rewinding arguments is you show that there is a way to like extract some underlying like classical proof string, or maybe quantum proof string. Right? And this requires just like querying the prover many times and just recording all the answers. Right? So that was what I was saying was the prior work. Like in these settings, you don't care about the prover's state really. You just care about recording lots of answers. And then the other setting where you use rewinding is when you're trying to think about the verifier. And why are you analyzing a verifier? Well, it's typically when you want to show that a protocol is zero knowledge. And in this setting, you need to basically simulate the verifier's view. And this is often done by rewinding, but doesn't necessarily require like recording a lot of answers. It just requires like producing like the right like conditional state, if you know what I mean. And so there's a lot more variety in like how people show things are zero knowledge. Like extract and simulate is not the only approach. There's many other different protocols and then different rewinding templates that have to work for it. Yeah, but I think that when proving soundness, there's really like one set of techniques, which is typically just like extract a lot of answers. Did that answer the question?
Thanks. Okay, I think this is a good place to stop. So let's thank Fermi again.